Hi, hello everyone. I am Muhammad Azriza Mirasid from University Malaysia Pahang, and I'll be presenting my paper today entitled Evaluation of DC Machine Armature Winding Temperature Estimation using temperature measured on brush and bearing. So for the presentation, we'll go through several introduction to understand the context and the objective of the study. Later, we'll go through methodology, explaining the experimental test setup and test procedures. And at the end, we'll try to look into the results and highlighting main results that we have managed to have. So in terms of context, basically what we're going to study over here is we know that it's very important to monitor the temperature of an armature winding of a DC machine. So it is especially for a machine that is constantly operating in a very dynamic manner, where a lot of torque are being driven, therefore a lot of current being drawn all the time dynamically. There is potential of high current inside the armature winding. Therefore, the temperature could rise, and we may have damages like the melting of insulation, therefore short circuit of the armature winding. So in order to do so, what we need to do is basically to monitor them. However, the monitoring method that we have today, if you want to do direct measurement, they are pretty expensive and complex. For example, using radiation thermometers, there are issues of emissivity and installation inside the casing of the machine. And there are other very advanced method like melting reagent, but these are complex and quite expensive. So what we do usually in terms of in literature is basically we estimate the rotor temperature. There are multiple methods, either based on parameter estimation. So this is basically by estimating the value of resistance through measurement of current and voltage, then deducing the value of resistance. By knowing that resistance varies in function of temperature, so we can predict the temperature by looking at the variation of this resistance. There are also other methods that based on thermal model, basically pre-develop a thermal model to basically estimate the temperature and therefore take the information in real time of current to compute using the model the temperature inside the armature winding. But this need, of course, the inconvenience is that to do it in real time, we will need a certain processor to be able to manage the computation at the same time of the utilization of the machine. And there are other models of on real-time measurement of this armature temperature based on hybrid methods. So what the question that we were asking is, rather than going through these estimations that are more or less complex, developing a model, for example, that could take a lot of time, could the armature winding temperature be estimated in real time just by looking at the temperature difference with other non-moving components? So for example, we have brush, bearing, and casing that can be easily instrumented with thermocouple. Can we, for example, say that the temperature of the armature winding is just equals to the temperature of the brush or temperature of bearing plus a certain estimator? So the potential advantage of if we could do this is that we could basically do a monitoring of temperature of the armature winding with a lower cost, and of course with a faster processing and less computation, because what's left to do is basically just to add a certain value of estimator to the temperature of the non-moving components. So the objective is basically first, we would like to evaluate the temperature distribution on 3 components that interest us, which is basically the armature winding, of course, and the other 2 components, non-moving component, which is the brush and bearing. From this distribution of temperature, we would like to identify the difference between the temperature of the armature winding and the temperature of the brush, as well as the difference between the temperature of armature winding and the bearing, and the potential errors of this temperature difference due to gradient on the components. And then we'll see whether the difference of this temperature can be used as basically indicator of the temperature of armature winding added to the temperature that is measured on brush and bearing. So in terms of methodology, what we do is basically in order to observe the temperature distribution, we are using a thermography. So the machine was basically submitted to a copper losses test or block rotor test. So we block the rotor and we increase the current from a range of current from a range of current until a maximum current with basically an acceptable value of temperature. So because we do not want to damage the machine, and the machine that we use is basically is the very common small 250 watt brush DC machine that we call MY1016. So it's a 24 volt DC machine, 250 watt. So what we do onto the machine is that the armature is pre-disassembled. So we execute the block rotor test, increase the temperature until steady state, and then what we do is that we disassemble the whole structure of the rotor with the armature winding. We hang it and we take a thermal image capture. There are also several thermocouple instrumented on the components to validate the thermal image that we've taken. So here, in terms of result, is basically the temperature distribution. The first one here is the temperature of armature winding, and here is the histogram representing basically the range of temperature from minimum to maximum. So here is the temperature of the brush, and here is the temperature of the bearing. And plotted at the bottom here are basically taken the data extracted from the histogram. So we took basically the maximum. Here is plotted the maximum temperature of each component. So the maximum is the temperature that can be found on far right of each histogram. And then we also calculate the average temperature of each histogram and plotted over here. The maximum temperature is of course in the armature winding, next followed by the temperature in bearing and brush. So we see here basically the temperature increase in the quadratic manner, because we know the losses is basically in terms of copper losses is Ri square. So it increased in a quadratic form, right? And here we basically plot what we call as temperature range. So temperature range is basically the difference between maximum temperature and minimum temperature for each component at different current. So the current that we managed to submit to the machine is from 1 to 5 amps. 5 amps is the highest, where the maximum temperature goes up to basically a bit lower than 75 degrees Celsius. So we see the temperature range also basically increase with the current. There are no particular trend in terms of which components has the highest temperature, right? So what we do next is basically we try to deduce the estimator of temperature. So what is temperature estimator? So the temperature estimated on the winding could be done by measurement of temperature on two components. One is either using temperature of the brush, or second is temperature of the bearing. So the temperature estimated using the estimated temperature of the armature winding using the brush, which is this annotation over here, will equals to the temperature of the brush. So this is the measured temperature plus a certain estimator. So this is what we call as estimator. So this estimator, what it is basically the difference between temperature of the brush and temperature of the bearing, temperature of the brush and temperature of the winding. So the same goes for an estimator using the bearing temperature. So the graph over here shows basically the difference of average temperature between the winding and the two component brush and bearing. So the red one is the difference of the temperature between the winding, armature winding and the bearing. The blue one is the difference between the temperature of armature winding and the brush. But nonetheless, this is only the difference in terms of average temperature. But looking at the gradient of temperature just now, we know that using average temperature is not totally precise. We may have an error induced by the gradient of this temperature, right? So we don't know if the temperature is actually maximum or minimum or the average temperature. So each component's temperature may have error due to this temperature gradient, which was quantified previously. So to take into account these errors, the error component are added to the temperature difference. So this temperature estimator over here, what is it equals to in reality? What we need to do to make it more precise to quantify the error. So the temperature estimator, let's have a look at temperature estimator using the temperature of the brush, is equals to the difference of temperature in average, the average difference temperature, which is this particular graph, plus a certain error. So this error here noted as delta, so delta winding brush for the estimator using temperature of brush, and delta winding bearing for the estimator using the temperature of the bearing. So how do we estimate them? We estimate them basically using we calculate the absolute error of each component added in quadrature. So what is absolute error added in quadrature? Is basically the sum of the range, the sum of the range of temperature of each component. For example, the error in the estimator using brush temperature is equals to the square root of the sum of the range of temperature of winding and the range of the temperature of the brush. So where does this range come from? This range comes from the one that we have calculated previously, that we have computed previously in the graph, in this graph that we can find in the 2 previous slides. So at the end, the complete winding temperature estimator will be equals to the difference of average temperature plus the error. So it will be equals to, if we look in terms of graph that we have previously, the graph of the difference in terms of average temperature plus the errors. So over here is basically the graph of the errors that is generated due to the distribution or the range of temperature on the component. This error is basically plotted versus current. So we can see that the temperature difference and error is increasing with current. The error as well is increasing with current. Maximum error at 5 amp is observed at 14.2 degrees Celsius and 12.9 degrees Celsius for bearing estimator and brush estimator respectively. So if we compare to the average temperature of winding temperature at 5 amp that we found just now, the potential estimation error that we can potentially have is up to 20.7% and 18.8% for brush and bearing estimator respectively. So here we can conclude that the temperature estimation using this particular method is too imprecise due to the large gradient, and unpractical as well, because we also need basically the information of current. We still need the instrumentation of current in order to compute this difference, because the error and the difference is varying in function of current. So that's all for this for our presentation. Thank you very much, and please contact us for further questions. Thank you.